Hi everyone, so I'm going to finish off talking about colligative properties by going through, hopefully it will be a fairly quick and straightforward video. So why don't we start off, I'm backed up a couple of slides from where we left off in the lecture, but we'll kind of make things flow together. So we'll be talking about colligative properties, right? So these are properties of a solution that depend on the amount of dissolved solute, but not necessarily, or actually not at all, its chemical identity. So this means if I had a 1 molar solution of glucose dissolved in water and a 1 molar solution of ethanol also in water, they would have the same properties despite ethanol and glucose being completely different compounds. So there's 4 colligative properties that we'll look at in this video. And those are going to be vapor pressure of solutions, and vapor pressure will always be lower than that of a pure solvent. Boiling point elevations for solutions, freezing point depression for solution, and then we'll briefly talk about osmotic pressure. So before we get started, we need just quick definitions. So when we're talking about solutes, so the particles that are dissolved in a solvent, we have 2 different types, volatile and non-volatile. So a volatile solute is going to be a solute that has a vapor pressure. So this would be something like water, ethanol, benzene, toluene. And then there's non-volatile solutes. And these are solutes that do not have a vapor pressure. And this would be something like glucose, sodium chloride, iron oxide, so that being like sugar, table salt, rust, things that don't have a vapor pressure. So the figure that we see on the right, we've seen this one before, where we were talking about what is vapor pressure, right? If we have a liquid inside a sealed container, the liquid will leave the liquid phase, go into the vapor phase, and the rate at which the particles leave and enter will hit equilibrium. And then these particles that are in the gas phase can exert a pressure, and we can measure that as the vapor pressure of the pure solvent. In this case, it's blue. Let's just imagine that it's water, right? Once we add a solute to this, and we can imagine that as those red spheres, whatever they are, maybe it's glucose, ethanol, something like that, right? Once that has been dissolved in the water, what we can measure is actually a decrease in the vapor pressure compared to the pure solvent. So we discussed this briefly in class, but the driving force for all colligative properties is going to be entropy. So we did out our little map with the squares showing that even just a small amount of dissolved solute will increase the entropy of the solution significantly. So when you have this high entropy solution down here, the driving force is going to be for the water to stay in that high entropy state, which then reduces the amount of water that's in the vapor phase, resulting in a lower vapor pressure. And so this was quantified by Raoul, in his name, Raoul's law, in which we can calculate the vapor pressure of the solution is going to be equal to the vapor pressure of the pure solvent times whatever the mole fraction of the solvent is. So let's start. Sometimes it's easier to see things of actually doing the math, right? So I believe we did this problem in lecture, but let's just quickly go through it again, right? So if we had 0.34 moles of sugar, so glucose, dissolved in 3 moles of water, the question is asking what is the vapor pressure of the resulting solution? And it gives us what the vapor pressure of water is at 25 degrees C, and that's 23.8 torr. So, like any problem that we're given, the best way to start, especially when we're going to get more and more complicated problems as we keep going into chapter 14, 15, 16, and 17, is to summarize everything that was in the paragraph as variables. And so that's what I've done here. So we have our number of moles of glucose, water, the temperature, and the vapor pressure of pure water as givens. We're being asked to find the vapor pressure of solution. And at least for us, we know what we're dealing with because we're under this heading of colligative properties and we only know one equation. We'll be looking at Raoul's law, which we just discussed in the last slide. So let's see how we should attack this, right? I'm asked to find PVAP of the solution. Luckily for me, that's exactly what this equation is looking for. That means I better know these 2 variables. PVAP solvent, well, my solvent's water, I got that. Chi solvent, well, I don't see chi in my givens, but since chi is the mole fraction, I do have the number of moles of solute and solvent, so I shouldn't be too hard to finish this problem off. So first we need to find the mole fraction of water. And so what you see here is we know chi of water, and we kind of broke this down in a very generic way when we're talking about units of concentration. I phrased it as, sorry, sometimes you'll see the mouse jiggle around. It freezes on me using this program and I have to wake it up, so sorry if it does that sometimes. But we have the mole fraction of water is just the total moles of water, the moles of water over the total moles of solution. The way I always kind of introduce chi is that chi of the thing we care about is our subscript. The thing we care about always goes on the numerator. So the thing we care about is the solvent. Solvent's water, so moles of water over total moles of solution. So my variables are n water and n glic. Plug in the information that the problem gave us, and we find out that the mole fraction of water is 0.898. The next thing we'll need to do is solve for the vapor pressure of the solution, because chi was the last thing that I needed to solve for, since pVap of the water or the solvent was given in the problem itself. So I plug in my units. Plug in my my numbers with the correct units. Right, chi is unitless. So my final answer is in 21.4 torr. Right, we don't really have an intuitive sense of how big the number should be. Right, but it should be, if it's vapor pressure lowering, lower than 23.8, and that it is. And actually, it should be around 90% of the total, or 10% less. That's rough. That is exactly, the mole fraction of that. Right, so we have 21.4 torr. So that example we had back here, if we go back here, we were looking at sugar. Sugar is glucose. Glucose, which we saw even back a further slide, a couple slides, right, is not a volatile solvent. The Raoult's law that we use, not the rules we use, but the way we used the equation in the last problem was assuming that it was a non-volatile solute. But what happens if we have a volatile solute mixed with a volatile solvent? Well, actually, the equation looks it's pretty much identical. If we have two volatile compounds mixed together, according to Dalton's law of partial pressure, the vapor pressure from whatever component A is, plus the partial pressure, the vapor pressure from component B, just going to be the vapor pressure of the solution. But how do I find the vapor pressure of A and B once they're mixed together? Because they're not going to be necessarily that of the pure A or B. Well, it's going to look like the pVap of pure A times the chi of pure A, which is exactly like the last equation we used. But now we're just going to tack on an additional pVap for B in the chi of B, because compound B is also volatile. So if you lost me on that, let me see if I can show you visually, right? So we're asking what the pVap of the solution is, and that's going to be this green line right here. So we see P total. This is a mixture of benzene and toluene, which are almost identical compounds. They literally differ by one methyl group, which is one carbon and 3 hydrogens. So if we look here, if I'm trying to find the vapor pressure of a solution in which I have a mixture of benzene and toluene. So if my benzene is, let's pick something easy. Let's do this. If my benzene has a vapor pressure of 40 and my toluene has a vapor pressure of 20, guess what happens when I add them together? 60 roughly, right? We're just using approximations here. So we see that Dalton's law of partial pressure holds. This, what I'm showing you right now, is an ideal case. Most mixtures will deviate from this and it requires theory beyond what we're talking about, but we're going to assume most things behave ideally and will follow this general pattern, that it's going to be the vapor pressure of whatever pure thing I'm looking at times its mole fraction plus the vapor pressure of the other component times its mole fraction. So again, sometimes this stuff makes a lot more sense with doing rather than saying. So let's do rather than tell. So let's take this problem. It says I have a solution is composed of 1.4 moles of cyclohexane, and it gives me the pure vapor pressure of cyclohexane right here, and 2.5 moles of acetone. And we're giving the pure, oops, why did that go forward? The pure vapor pressure of acetone. And we'll be using the little not symbol to indicate the pure compound, right? So this is going to be a mixture of cyclohexane and acetone, so their vapor pressures will not be equal to their pure vapor pressures. And we're going to have to find out what those are. And it's asking me, what is the pVap of the solution, right? So again, we're going to organize our givens in finds. I have the number of moles of cyclohexane, of acetone. I have their pure pVaps, and it's asking me to find the p-vap of the solution. We only have one equation so far. This looks, if I cover this up right here, it looks exactly like the Raoult's law that we did in the previous equation. This just has, again, two volatile compounds, acetone and cyclohexane. So let's see how we're going to attack this. First, we're going to need to find the mole fraction of both cyclohexane and acetone. So we go around the same process that we did in the previous glucose water example. And so we have the moles of what I care about over the total moles, moles of what I care about over the total moles. So chi-cyclohexane is 0.359 and chi-acetone is 0.641. A quick check if we have time, right? If we're doing things, checking, dotting our I's and crossing our T's, we can double check the mole fraction. And the way it should work out is that all mole fractions, no matter how many I have, should total to unity, which means 1. So the chi of cyclohexane plus the chi of acetone should total to 1. Double check, 0.359 plus 0.641 does indeed total to 1. Sometimes when you do these problems, occasionally you'll get it close to 1 because you're dealing with actual numbers, but theoretically it should total to exactly 1. So now, if we have our chi's, let's just take a look at our equation, right? We're looking for p-vap of the solution. The problem gave me the p-vap of pure cyclohexane. We just solved for the chi of cyclohexane. The problem gave me the pure vapor pressure of acetone. I have the chi of acetone. At this point, it becomes plug and chug. Plug that in, times it by my cyclohexane, plug in my vapor pressure, times my chi of acetone. Add those two components up, we get 180 torr. Again, we're not going to get a sense if we did this right. There are sometimes we do problems like, okay, that makes sense. Here, all we really can make a fairly good estimate that it's somewhere between 97.6 and 229.5, and 180 is. So that's giving us an indication, at least we're in the ballpark, and I guarantee we did this one right? So that's like a check you could do if you're on an exam or a quiz to make sure the answer makes sense. And so that pretty much covers what we're talking about in terms of vapor pressure lowering, right? When we mixed anything together, the vapor pressure of the solution will be lower than the vapor pressure of the pure solvent. So let's move on to our second and our third colligative properties, which we're going to kind of treat together because they're going to be the same equation, roughly. It's a slight difference, and we'll talk about that. But it's in terms of changing the temperatures at which phase changes occur at. And it's always the case that boiling point will increase, so it's a boiling point elevation, and it will always be a freezing point depression, so the freezing point will always go down. And we talked briefly in class about this. It's like if we actually could get winter this season, right, we'd have snow on the ground, and occasionally you might go out there and throw ice melt down. Well, it's not necessarily melting because you threw the salt down and heat was released. It's because when you added salt to the ice, it actually creates a solution of sodium chloride that the freezing point has now been depressed or lowered beyond the temperature that's outside, so it remains liquid. And so it's actually melting because of the colligative properties. The entropy of that solution is increased so much that it's not going to freeze at the temperature it is outside. So let's see if we can put this idea of freezing point depression and boiling point elevation into actually doing an example with this, right? So solutions of ionic substances often have vapor pressure significantly lower than predicted. This is because of ion dipole forces between dissolved ions and the polar water molecule, and that the interaction between ions and pure water is so strong, the polar water, right? What we need to talk about first, if we're going to be talking about dissolving salts into water, is introduce a new concept called the Van't Hoff factor. So a Van't Hoff factor is going to, because we're looking here, if we have something that's deviating from ideality, these ionic substances, their vapor pressure is significantly lower than predicted, well, that's telling me that the colligative properties are going to be affected by strong ionic substances like potassium chloride, sodium chloride, right? So a Van't Hoff factor is represented by the letter I. It's usually given as an italic I, and it's the moles of particles in solution dissolved by the moles of solute dissolved. It's a little bit abstract. It's way easier to see as a chemical equation. The Van't Hoff factor of sodium chloride is roughly 2. The theoretical maximum is 2. Why? Let's take a look at this. The number of moles, so imagine I'm making a 1 molar solution. So I add 1 mole of NaCl to a liter of water. My NaCl, that's the number of moles of solute I tried to dissolve. I tried to put a mole into solution. Oops. And when it does dissolve, it actually turns into 2 things. Moles of particles in solution. So I put in one thing and it dissolves, and it's effectively acting as 2 separate things. So if you think about that, if you dissolve something like glucose, which doesn't dissociate, it's just basically you add 1 molar solution, you have 1 mole of glucose, it behaves as 1 mole of things. You make a 1 mole solution of NaCl, it actually behaves as 2 things. It's like having a 2 molar solution of stuff. So the Van 't Hoff factor is basically a correction factor for the concentration of ionic substances. For sodium chloride, the predicted value for I is going to be 2. In real life, it's closer to 1.9, and it does depend on experimental conditions, but it's basically saying I can't max out over 2 because the most you can dissolve is 2. There's a small, tiny portion actually floating around in solution behaving as NaCl. So let's do a couple of examples of the Van 't Hoff factor of like estimating the maximum, and then what we're going to do is take this idea and apply it to freezing point depression and boiling point elevation. So let's take the idea of potassium fluoride, or Kf. So if I was going to estimate this Van 't Hoff factor, well, take a look at that. Kf solid, I put it into water, it turns into K plus and F minus. The theoretical maximum is 2. In real life, it's probably a little lower, but it can't exceed 2. Take a look at magnesium chloride. MgCl2, I dissolve that into water. I get 1 magnesium 2 plus and 2 Cl minuses. The theoretical maximum for the Van 't Hoff factor, 3, because I got 1 magnesium 2 plus, 2 chloride minus, 3. Glucose. If I take glucose, which is C6H12O6, dissolve that into water, it doesn't dissociate. It effectively acts as one thing, so the Van 't Hoff factor would be 1. Though usually you don't apply Van 't Hoff factors for things that don't dissociate. And let's not forget about polyatomic ions. So let's just do one quick tough one, quote-unquote tough one. Try this one on your own, maybe pause the video for a second. Remember what ammonium is, that's a polyatomic ion, and phosphate, that's another polyatomic ion. Oops, I didn't change. I originally was going to do sulfate. Forgot to change this one. This should be phosphate. But if we look here, we have ammonium. Again, in your mind, this S becomes a P, right? So we have ammonium phosphate solid. I put it into water. I end up with 3 ammoniums, 1 phosphate. That behaves as 4 components. And the I would be equal to a theoretical maximum of 4. Like I said, in real life, the numbers could be lower and usually are, but we're talking about theoretical maximum. So let's see how this affects solutions, right? So what we're going to find out is a book gives us 4 equations. It's basically the same equation, but let's take a look at it. Let's start with this one here, with non-electrolytes. So if we remember what a non-electrolyte are, basically this is a compound that doesn't dissociate in water. So this would be like our example of glucose here. It's not dissociating, it just is solvated. So theoretically, if the I were here, it'd just be the number 1. And it actually would look like this equation here, right? If we're looking at the temperature change of boiling point, the only difference between a non-electrolyte and electrolyte is that Van 't Hoff factor. So if you're comfortable with putting in the number 1 for non-electrolytes, you only need to know this equation, not both. So if we look at the freezing point depression, it looks almost identical. The change in the temperature of the freezing point is going to be equal to some constant, just like we have up here. Some boiling point has some constant, times its molality. The only difference between a non-electrolyte and electrolyte, again, is this Van 't Hoff factor. And if you're comfortable with non-electrolytes having a Van 't Hoff factor of 1, again, you just need to know one equation. So it doesn't get much harder than that. If you're looking for a change, say in boiling point, it's just the constant, and you'll have to get that off of a chart, and I'll give that to you. The molality of the solution, sometimes we use the letter B, the book uses the letter M, so that's what I have here. And the Van 't Hoff factor. So pretty much, I have to give you 3 of these 4 things to solve for the 4th, right? It's actually not too terribly difficult to do. So again, sometimes doing, again, is better than showing. So let's give it a shot. So it says, what is the freezing point in degrees Celsius of a solution prepared by dissolving 7.40 grams of magnesium chloride in 110 grams of water? It says the Van 't Hoff factor for MgCl2 is 2.7, and then I give you the freezing point depression constant of 1.86 degrees Celsius kgs per mole. So the first thing we can do is we got to convert our grams of magnesium chloride to moles magnesium chloride. Because if we look back at our old equation, I'm going to need a couple of things. I was given, if we're looking freezing point depression, I was given the K. I'm given the I. But what I need to figure out is molality, right? Molality is moles per kilogram. So I need moles of solute, and there I got it for MgCl2. Because I'm trying to solve for that molality to plug into the equation, there's my moles of solute over my mass of the water. I got to convert the mass of water from grams to kgs first. My grams will cancel out. I'll end up with units of moles per kilogram, which is the units for molality. So it's 0.71 molal solution. Calculate the freezing point depression. There's the constant I gave you. There's the molality we calculated. And there's the Van 't Hoff factor I gave you. Multiply everything out. Make sure our units cancel. Mole and mole cancel. Kg and kg cancel. Van 't Hoff factor is unitless. I'm left with the units of degrees C. Multiply it all out. 3.6 degrees Celsius. We got to stop and think for a second with these problems. Is it boiling point elevation, or am I looking at freezing point depression? So it's freezing point depression, right? Here, I need to be aware that the temperature at which the water, in this case, or the solvent is going to freeze, you need to take its normal freezing point. Water freezes at 0. Right? Ethanol freezes at negative 114. We need to make sure we know the pure freezing point. So in this case, water is 0. We minus the freezing point depression from it because it's going down. It's being depressed. The new freezing point is not positive 3.6. It is negative 3.6 because it is lowered from its original freezing point of 0. Oops, okay. I guess I was getting ahead of myself on that. So it doesn't get much harder than that. It's recognizing what direction I'm going in. You could do a boiling point elevation problem. I'll give you some of those to practice for our quiz on Friday. But that will be part of, I think it's already part of the practice problems. So the last thing I want to touch on is osmosis and osmotic pressure. We're going to more concentrate on the concept of what this is rather than the equations. The equations work, but it makes a large amount of assumptions because we're going to be using essentially the ideal gas law for liquids. And so it works if it's theoretically ideal, but in real life it deviates significantly. So we're not going to concentrate mostly on the math, more on the phenomenon of osmotic pressure. So osmosis, what is that? So it's the passage of a solvent through a semi-permeable membrane from the less concentrated side to the more concentrated side. Effectively, what the water is trying to do, or the solvent's trying to do, is dilute the more concentrated side. And a semi-permeable membrane just means it lets some things through, but not others, right? So, like, your cells can be, in certain situations, can be semi-permeable, where water and other nutrients can passively diffuse through the membrane. So when you have this semi-permeable membrane and then two solutions in contact through it, what arises is something called osmotic pressure, which we represent with the Greek letter capital pi, right? So it looks like, little lowercase pi, 3.14. This is capital pi. So it's the amount of pressure necessary to cause the osmosis to stop, right? Or the amount of pressure necessary to achieve equilibrium passage of solvent molecules through a semi-permeable membrane. So what does that look like, right? We're going to see these things. We have definitions, but it's easier to see, right? So we'll start here, right? We have this gray line, which is a semi-permeable membrane. The red dots are going to be our solvent particles, which are going to be H2O in this example. The blue particles, they can be whatever you want. Maybe it's salt, maybe it's glucose, maybe it's a protein, I don't know, right? So what we have here, though, is something where it's just pure water, and over here we have a solution. So what the water is going to do is effectively try to dilute these solute particles. because it's trying to reach equilibrium. It wants everything to be the same, but if only water can move through the semi-permeable membrane, it's impossible for these blue dots to move back and then try to hit equilibrium. So what happens is this water keeps going through and trying to dilute the solute. And what that does is it actually raises the amount of liquid that is in this part of the container. So what is the osmotic pressure? Well, this is not really the pressure. It's the pressure you exert to push this back down, to get things back to where they were. So it's basically, we really can't read this pressure, but I can read the pressure pushing down, and then it will equal that. It will be equal to this pressure. And so this is what osmotic pressure is, right? And so this is what I was getting at, is that it looks like PV equals nRT if you substitute P for pi. We just have the Van 't Hoff factor in there in case we're dealing with ionic solutions, but it looks a lot like PV equals nRT, right? I just want you guys to see this. For me, I'm not interested in if you can use it because there's a lot of assumptions and it's not a particularly accurate equation to use, right? But the theory of it is actually quite important, right? So some terminology when talking about osmosis, right? We're going to have isotonic solutions. That means if I'm looking back here, the two solutions that are separated are going to be equal concentrations of solvent and solute, so the osmotic pressure is going to be equal. So the passage of water through the semi-permeable membrane is equal, and nothing happens. A hypertonic solution, this is going to be when the solution has higher concentrations of solute, and the water will rush from the pure solvent to try and dilute that. And that's what we saw here, right? There's our hypertonic solution. It has more solute molecules in it than the pure, and so there's a migration of the water to try and dilute it. And a hypotonic solution, so hyper being above tonic, so above concentration, below concentration is a hypotonic solution. That means the solution that you're looking at actually has a lower concentration of solute, and so the water will leave and try to dilute the higher concentrated solute. Again, I can explain these things, you can read it. It's easier to see if we talk with an example, right? So if we have an isotonic, this is a red blood cell, which water can passively pass through the cell membrane. And so if you store it in an isotonic solution, which is basically like your blood, the concentration of stuff outside the cells is equal to the concentration on the insides, or at least the sodium concentrations, and certain other key nutrients are the same. So the water can passively diffuse in and out, but the cell keeps its shape because the osmotic pressure is equal on the inside and outside. What we have here, though, is say if you ate a boatload of salt and somehow made your blood very, very salty, right? So a high solute concentration outside this red blood cell, this is going to be a hypertonic solution surrounding the blood cell. That means there's too much salt. So what will happen is the water will rush out of the cell to try and dilute that salt. What that ends up happening is the cell actually gets crushed by the pressure on the outside because all the water is rushing out. And then the opposite, and this has actually happened a couple times in the news, if you drink way too much water way too quick, you dilute the salt concentration in your blood. What ends up happening is the salt concentration inside your red blood cells is actually higher than it is outside. The water rushes from your blood, the I don't know, I'm not whatever the liquid part of your blood, right, will rush inside to the red blood cells, and it actually causes them to burst because all the water is rushing in and they literally physically explode. And so that's what we have here. Oh, for some reason I screwed up the picture here. Damn it. All right. Oh, maybe? Yes. There we go. We have our red blood cells under an isotonic solution. But if we change that, we can actually see here, this is a burst red blood cell because there's a hypotonic solution around it. Hypotonic solution around it. The water is rushing out and it explodes. And so that's all I really wanted to get to in terms of colligative properties. The video is a little longer than I thought, around a half an hour. So hopefully this guy helped you solidify the idea of colligative properties. There are plenty of practice problems. Give those a shot. You guys will have, so today's Monday, you'll have until Friday to get ready for the exam. We can spend a little time on Wednesday if you'd like to answer some of the questions, but we still need to keep moving forward with Chapter 14. I've also attached, this is already on EC Learn. There's a bunch of practice problems already on EC Learn. So if you want those too, with some step-by-step solutions, those are there as well. Plus the already practice problems that I handed out to you guys earlier. So I'll see you all on Wednesday, and I guess that's it.